Okay. So students, we had discussed in the morning IR spectroscopy and principle of IR spectroscopy. Okay. Now so we have to start from here. Okay. So I'll adjust this bar here. Okay. So in the same IR spectroscopy, see, organic compounds, we know that compounds, but we are discussing about mainly about organic compounds. Even inorganic compounds, they also absorb IR radiation or electromagnetic radiations. Okay, so in organic compounds, they absorb electromagnetic energy in the IR region. They are able to absorb. Okay, IR does not have sufficient energy to cause excitation of electrons. They do not have sufficient energy. Okay, as in UV visible region. However, it causes atoms and group of atoms of organic compounds to vibrate faster the covalent bond which connect them. Faster these bonds in organic compounds, the atoms which are bonded through this bond, these atoms, they start vibrating through this bond. Okay, so they start vibrating. Okay, and these vibrations may be very fast. Okay, faster the covalent bond, this covalent bonds, this bond through these bonds, okay, they start vibrating. Okay, in IR region, the vibrations may be there are different modes of vibrations. Okay, we'll discuss about these different modes of vibrations. Okay, in organic compounds. So a molecule in its ground state possesses three energy levels. A molecule in its ground state possesses three energy levels, which are electronic, this one we'll discuss, this electronic energy levels, vibrational and rotational energy levels. Vibrational and rotational energy levels. There's three a molecule in its ground state possesses three energy levels. Okay, we have already discussed these three levels. Okay, what happens? Absorption in the IR region is due to the change in the vibrational and rotational levels. When there is change in vibrational and rotational levels, it means it has absorbed, the molecule has absorbed in IR region. The absorption in IR region has taken place. Okay. When an electron absorbs less energy, when an electron absorbs less energy, rotational transitions take place. Lesser energy, rotational transitions take place. The spectrum observed is called rotational spectrum. In that case, the spectrum which we get, or the spectrum which is observed, is known as rotational spectrum. Okay, and it is observed in far IR region, 25 to 3 up to 25 to up to 400 micron. So in far IR region, okay. But when the electrons absorb still higher energy, higher than this, vibrational transitions take place, which is accompanied with rotational transitions. So there will be rotational transitions as well as vibrational transitions. The spectrum observed is called vibrational rotational spectrum. In that case, it is known as vibrational rotational spectrum. Okay, this is observed in near IR region, 2.5 to 25 micron, near IR region. Okay, this near IR region. Electronic transitions take place at higher energies. These are not seen in IR. Okay, so which the transitions which are taking place at very high energies, they are not observed in IR region. Okay. So what is the criteria for a compound to absorb IR radiation? It is like selection rule. Okay. So criteria for a compound to absorb a IR radiation. there must be a change in its dipole moment upon absorption. If there is no change in dipole moment, it will not show. It will be termed as IR inactive. Okay. So there must be a change in dipole moment. A molecule can only absorb IR radiation when its absorption causes a change in its electric dipole. Electric dipole. Okay. So if there is no electric dipole change, if electric moment, if it is zero, then it is IR inactive. IR inactive. Okay. In this case, it will be IR inactive. There must be a polar bond, okay, in the molecule. A polar bond is usually IR active. A polar bond is usually IR active. So if the molecule has a polar bond, if it has polarity, it will be IR active. Okay. A non-polar bond in a symmetrical molecule will absorb weakly or not at all. A non-polar bond in a symmetrical molecule will absorb very weakly, okay, or negligible, or not at all. It will not absorb. Okay. Now, few important terms which we should know, and it is very important as far as examination is concerned: molecular vibrations. So we are going to discuss the fundamental molecular vibrations a molecule possesses. Okay. So this we are mainly concerned with fundamental vibrations. Non-fundamental vibrations we don't have to discuss. Okay. This is not there in our syllabus. So we are mainly concerned with fundamental vibrations. Non-fundamental vibrations we are not going to discuss. So in molecular vibrations, we have fundamental vibrations and non-fundamental vibrations. So in this non-fundamental vibrations, overtones, combination tones, and Fermi resonance, this is not there in our syllabus. So we are not going to discuss this at all. Okay. Now, in fundamental vibrations, again, these fundamental vibrations, they are categorized in two categories. Okay. Two classes: stretching vibrations and bending vibrations. Stretching vibrations and bending vibrations. We have this stretching vibrations and bending vibrations. Now, this again is subdivided into two classes. This stretching vibrations. We have symmetric stretching and asymmetric stretching. Symmetric stretching and asymmetric stretching. Okay. Now in bending vibrations, we have, again, it is classified into two groups. It has been divided into two groups: in plane bending and out of plane bending. In plane bending, again, scissoring and rocking. And out of plane bending, we have wagging and twisting. Wagging and twisting. So fundamental vibrations divided into two categories: stretching vibrations and bending vibrations. Again, stretching vibrations, we have symmetric stretching and asymmetric stretching. And in bending vibrations, we have in-plane bending and out-of-plane bending. In plane bending, we have scissoring and rocking. And in out-of-plane bending, we have wagging and twisting. We're going to discuss these, okay, one by one. Now, so already we have discussed molecular vibrations. There are two types of molecular vibrations: stretching and bending vibrations. Stretching vibrations, stretching vibrations, vibration or oscillation along the line of bond. Along the line of the bond. Suppose this is, okay, we'll draw this carbon-carbon double bond. Okay, so vibration or oscillation along the line of the bond, along the line of the bond, along the line of the bond. Okay, change in bond length. Suppose it will vibrate, it will come forward and come, I mean, it will stretch, okay, and it will compress. So there will be change in bond length. Obviously, there will be change in bond length occurs at higher frequency. This is up from 1250 to 4000 per centimeter. Okay, higher frequency. These are two types. We have already discussed symmetrical stretching and asymmetrical stretching. Okay, symmetrical stretching and asymmetrical stretching. Okay, so we are going to discuss these two, symmetrical and asymmetrical stretchings. Now we can see here symmetrical and asymmetrical stretchings. Symmetrical stretching. This is symmetrical stretching, the first one. Okay. See here. Both bonds, we have a central carbon, and these are two atoms, and these two atoms, these are bonded to this central atom. Okay. Now we can see here. Okay. Both bonds increase or decrease in length simultaneously. They will increase and they will decrease, stretch and compress simultaneously. The same length goes out, comes back, goes out, comes back. It is symmetrical. Symmetrical, same length going out, coming back, going out, coming back. So both bonds increase or decrease in length simultaneously. Simultaneous. Okay. Now the second one, asymmetrical stretching. What we can clearly observe in this animation, what is happening in this, one bond length is increased. We can see here one bond length increases and the other is decreased, the other decreases. So one increases, this will decrease, this will increase, the other one will decrease. We can see here, this is going, this is increasing, this is decreasing. When this is increasing, this one is decreasing. Okay, you can observe clearly. Okay, so this type of stretching is known as asymmetrical stretching. Asymmetrical stretching. Understood? We have two types of stretching, this symmetrical stretching and asymmetrical stretching. Symmetrical, asymmetrical stretching. Okay. Now the second one, the bending vibrations. Vibrations or oscillations not along the line of bond. Not along the line of bond. It is not along the line of bond. Also called as deformations. They are also known as deformations. In these vibrations, bond angle is altered. Bond angle is altered. Suppose we have this. So 1, 2, 3, 4. So this, they are vibrating or they are bending. So bond length, this bond length, it increases or decreases. Okay. Now, at low frequency, it happens at low frequency around 666 to 1400 per centimeter at low frequency. These are also of two types. In plane bending, for example, scissoring and rocking. In plane bending, scissoring and rocking. Out of plane bending, that is wagging and twisting. Wagging and twisting. Wagging and twisting. Okay. Wagging and twisting. So we can see here in plane bending. In plane bending, scissoring. This is an in plane bending. Two atoms approach each other. Bond angles are decreasing. Two atoms, they approach each other. Okay, we can see here, this is not along the bond. Okay, these two atoms, deformations, we can say, kind of deformation. Okay, so these two atoms, they are approaching each other, and in this case, this bond length is increasing or decreasing. This bond length, it alters. Okay, now rocking. Movement of atoms takes place in the same direction. The same direction. Movement of atom, same direction. See, once here, the same, but there is no change in the angle. We can see here. both are the same position, but both at a time they are moving backward and forward, backward and forward. Okay, see here, rocking. Movement of atoms take place in the same direction. Here, same direction, same, okay, same direction at a time. Okay, movement of atoms takes place in the same direction. Now, out of plane bending, out of plane bending. That were those were in plane bending, and these are out of plane bending. Out of plane bending. So in this we have wagging and twisting. Wagging and twisting. Wagging and twisting. So in wagging, what happens? Two atoms move to one side of the plane. Two atoms move to one side of the plane. They move up and down the plane. They move up and down the plane. Two atoms move to one side of the plane. Suppose this is a plane. Okay. If we have a plane here, we have a plane here. Okay. So suppose this is the plane of the molecule carbon carbon. Okay. So below the plane and above the plane. So two atoms move to one side of the plane. The two atoms move one side of the plane. Okay. So two atoms move to one side of the plane. They move up and down the plane. They move up and down the plane. One time up and one time down the plane. Two atoms move to one side of the plane. First up inside the plane and outside the plane. They move up and down the plane. Okay. Now the second one, twisting. The twisting. One atom moves above the plane and the other atom moves down the plane. So it is twisting. One atom will move above the plane and the other atom will move down the plane. Then the other atom will move up the plane. The first atom will move down the plane. It is like this. Okay. So this is known as twisting. It is known as twisting. Okay. So in wagging, both the atoms, they move to one side of the plane. So they move up at a time. They move up and they move down the plane. They move up and they move down the plane. Okay. In twisting, what happens? One atom will move above the plane and the other atom will move down the plane. Okay. Or the below the plane. Up the plane and below the plane. Okay. So this is twisting. In wagging, both two atoms move to one side of the plane, either up or down the plane. Okay. Now again we can see here molecular vibrations. We have this methane molecule. Okay. Carbon, 4 hydrogens. This is symmetrical stretch. Symmetrical stretch. All the hydrogen, this bonds, they stretch together. Okay. The bending modes of, okay, these are the bending modes of, like this bond bending modes are here. Okay. This is asymmetric stretch. In this we can see here this hydrogen is coming down and rest they are going away. They are stretching and the one is compressing. It is coming down. Okay. Now symmetric bend and asymmetric bend, or in these bending vibrations in plane and out of the plane. Okay. Now the other important factor, number of vibrational modes. This may be asked for 2 marks. How many number of vibrational modes one molecule may have? Okay, it may have. Okay. So this number of vibrational modes. Okay. So for linear molecules, number of types of vibrations is, this is the formula. You should remember this formula. students. For linear molecules, it is 3n minus 6. 3n minus 6 number of fundamental vibrations. Okay. For linear molecules, this is for linear molecules. Number of types of vibrations will have, it will have, or they will have 3n minus 6 vibrations. And for, no, this is for non-linear molecules. Sorry. This is for non-linear molecules. Number of vibrations will be 3n minus 6. And for linear molecules, number of types of vibrations will be 3n minus 5. 3n minus 5. Linear molecules. This is for linear molecules. Okay, understood? This is for linear molecules. Now, we'll take one example. Okay. Okay. This is not, we are not concerned with these things. Okay. We already know these things. So we are concerned with these two things. Number of vibrations in non-linear molecules and number of vibrations in linear molecules. Hello? Hello? Mute yourself. Roll number. Okay. If you have doubt for G2. Roll number 67. 467.
Yes, sir. Yes, sir.
You have any doubt? Okay. So we are mainly concerned with number of vibrations in non-linear molecules and number of vibrations in linear molecules. So we have taken an example of linear molecule, HCl. HCl is a linear molecule. So according to this formula, 3n minus 5, 3n minus 5. HCl, two atoms are there. HCl, okay. So 3n is number of atoms, and n indicates number of atoms, okay. Number of atoms. Number of atoms, okay. So in HCl, we have 3 into 2, 6 minus 5, 1. So only one type of vibration. Okay. Now this one. Carbon dioxide. How many atoms are there? 3 atoms are there. 1 carbon, 2 oxygen atoms. So, and it is a linear molecule. Remember, it is a linear molecule. Carbon, carbon, this and this. It is a linear molecule. Though it is polar. Okay. It is a linear molecule. So we have linear for linear molecule 3n minus 5. 3n is 3. So 3 into 3, 9 minus 5, 4. So we have 4 modes of vibration. In carbon dioxide, we have 4 modes of vibration. This you don't have to draw. These modes of vibration you need not draw for in examination. You just have to calculate the number of vibrations in examination. Understood? You just have to calculate the number of vibrations a molecule will show in IR spectra. Okay. Now we'll see other. Okay. Now already we have discussed. Okay. More things. IR active vibrations. In order for molecule to absorb IR radiation, we know vibrations at same frequency as in light, but also must have a change in its net dipole moment as a result of the vibrations. So for example, in carbon dioxide, as we know, there are four fundamental vibrations. It will show 4 fundamental vibrations. Okay, 4 fundamental vibrations. We can see here which vibration will be IR active and which vibration will be IR inactive. Okay, so we can see here this symmetric stretching. In this symmetric stretching, okay, the net dipole moment will be 0 and it will be IR inactive, and it will be IR inactive. Okay, it will be IR inactive. Okay, now the other one in here, see, asymmetric stretching, the dipole moment will be more than 0, so it will be IR active. Similarly, the other 2 modes, okay, there is the net dipole moment is more than 0, so these are IR active. So only this one will not be observed. but these three vibrations will be observed in IR spectra. These will be observed in IR spectra. Okay. Now, so quickly we'll discuss the applications of IR spectroscopy. Okay. Applications of IR spectroscopy. Students, are you listening? Hello? Are you on the
Yes,
same
sir.
note?
Yes, sir.
Okay. So hope you have understood the previous topics which we have discussed. Now, the important thing, applications of IR spectroscopy. Okay, you should remember these applications. Okay, identification of substances. It can be used for identification of substances. To compare spectrums, we can compare spectrums of different molecules, and we know that no two samples will have identical IR spectrum. Okay, no two molecules will have same identical IR spectrum. So what is criteria? Sample and reference must be tested in identical conditions like physical state, temperature, solvents, etc. These must be same. Okay. The fingerprint region 600 to 1200 per centimeter. Small difference in structure and constitution of molecule result in significant changes in the peak in this region. Hence, this region helps to identify an unknown compound. We can easily identify any unknown compound in this region, in the fingerprint region. This region is known as fingerprint region. We can easily identify any unknown compound. Okay. We can study progress of reactions. We can study the progress of any reaction, organic, any reaction. Okay. Observing rate of disappearance of characteristic absorption bands in reactants. Rate of increasing absorption bands in products of a particular product, for example, this carboxyl, this hydroxyl OH. This is the absorption peak, 300, 3600 to 3600, 500 per centimeter. This is the characteristic of this group where it absorbs. And this carbonyl, as I discussed in the morning, 680 to 760. So this is, so what we can do, measure the degree of polymerization in chemical compounds. So we can also do this. We can measure the degree of polymerization in chemical compounds. We can do determination of molecular structure also. We can determine the molecular structures. Okay. So this is done based on the position of absorption bands in the spectrum. How we are able to determine the molecular structures? It is based on position of absorption bands in the spectrum. Okay, like this one, 717. An absence of band of a particular group indicates absence of that group in the compound. If this band is not there, it means this functional group is not there in the compound. Detection of impurities. We can detect impurities determined by comparing sample spectrum with the spectrum of pure reference compound. Suppose we have a pure compound and we already have the spectrum of a pure compound. Now we have a compound. If we find any other spectra, so it means it has an impurity. So like ketone impurity in alcohols, we can find out easily. If ketone is present in alcohol, it will show another spectrum. Okay. And detection is favored when impurity possesses a strong band in IR region where the main substance do not possesses a band. For example, impurity in beeswax with petroleum wax. Okay. So you remember this one. This one is easy to remember. Okay. What other things we can do? We can monitor the structural plasticity of plant cell walls. So we can do this also. monitoring the structural plasticity of plant cell walls. We can do this also using IR spectroscopy. Okay. Protein quantification. The other thing which we can do, protein quantification. IR spectroscopy is one of the most well-established techniques for the analysis of protein structure. So this is used for elucidation of protein structures. Okay. By measuring amide bonds in protein chains, we can accurately quantify an intrinsic component of every protein. So it is very important tool for quantification of protein structures or for elucidation of protein structures. Okay. Blood glucose, non-invasive blood glucose monitoring, non-invasive blood glucose monitoring. This also we can do. Near infrared spectroscopy is used across the earlobe to measure blood glucose, okay, to measure glucose. Amount of near infrared light passing through the earlobe depends on the amount of blood glucose in that region. The earlobe was chosen due to the absence of bone tissues and also because of its, okay, this is not required. So what we can do, we can simply, you can write that blood glucose, it can be used for non-invasive monitoring of blood glucose level. Non-invasive monitoring of blood glucose level. Okay, how it is done, we are not concerned with this. Okay, some other applications. We have only a few minutes. So where else it is being used? Determination of unknown contaminants in industry using FTIR. So here it is very useful for industry. Determination of unknown contaminants in industry using FTIR. Determination of cell walls of mutant and wild type plant varieties using FTIR. Biomedical studies of human hair to identify disease states. Okay, this is also being done. Disease states we can identify. Identifying or odor and taste components of food in food industry. Okay, we can identify the odor and taste of food components. Determine atmospheric pollutants from atmosphere itself. This is being done. Determination of atmospheric pollutants using spectrophotometers, IR spectrophotometers. Now, other thing, examination of old paintings. We can examine old paintings also using IR spectroscopy. Now, the last one, it is also used in forensic analysis in both criminal and civil cases. Both in criminal and civil cases. Example, in identifying polymer degradation, in determining the blood alcohol contents, etc. So in forensic analysis, it is being used. This tool is being used. It is very helpful, okay, for criminal and civil investigations, criminal and civil case investigations, okay. So this is all about IR spectroscopy. Already we have discussed the selection rules, okay. So we are